All right, good morning. It is Thursday, November the 19th, 2 days before a nice Thanksgiving break. Okay, I will be posting your e-assignment during what's next, third period today. And so that's not going to be due until the Monday after Thanksgiving. So you have lots of time to do it. Hopefully it's not going to take a tremendous amount of time. And we might actually start working on some of it Friday in class, okay? Because the first part of it is gas law problems. And so we'll have some time maybe to do that. All right, so yesterday we went through Boyle's law. Which basically said P1B1 is equal to P2B2. What's constant here?
Temperature.
Constant temperature. So when we made the shaving cream expand, okay, the volume increased as the pressure was decreased, but the temperature was remaining constant. I mean, we were basically room temperature the whole time. We didn't do anything with the temperature. Then we had Charles' law. Which says V1 over T1 is equal to V2 over T2. At constant what? And that's with a hot air balloon. Okay, we have the big fire, heats up the balloon, spreads it out, but it's going to spread out to keep the pressure the same inside and outside. It's a constant pressure thing. So it expands to keep the pressure constant. Now what must be true on this one? Temperature must be and we say Kelvin is equal to degrees Celsius plus 273, so we just remember that. Okay? Then we had Gay-Lussac's law. Which says what? Okay, at constant
volume.
Okay, so that's like throwing an aerosol can into a fire. The aerosol can's got a constant volume, and so as you increase the temperature, the pressure increases proportionally until the can can't hold anymore and it blows up, and it's really fun. Don't just throw it like into a bonfire if you ever attempt to do this at home, even though I don't recommend it, because then it's like shrapnel just spreading. When I did it as a kid, we always had like a burn barrel, and so everything would shoot up and not out, and so and then it also magnified the noise.
But the risk makes it more fun.
Until it doesn't.
Also, you could
So you throw it and run, maybe.
You could have your friends around your fire.
Yeah. So these two are what type of proportion? These are directly proportional. If I turn the camera just up here this way. Which one this is? Inversely proportional. Proportional. Okay? So as one goes up, the other one goes down, but here as one goes up, the other goes up. So we know how those work. So then when we combine them all together and don't keep anything, what's the combined gas law going to be?
P1 and V1 over T1.
Now, I do believe that Mr. Graber, go ahead and gives it to you kind of in the cross-multiplied version. And those of you that had him, and so you say P1 V1 T2 is equal to P2 V2 T1, but that's just after you cross-multiply and set it up. But the reality is that combining these if with constant temperature, we get Boyle's law, constant pressure, we get Charles' law, constant volume, you get Gay-Lussac's law. So really, this is the only one that you need to know. Now, these are all on your equation sheet, so you don't ever have to memorize the equations. Now, today we want to add in, well, what happens, there's nothing as far as quantity in this, okay? So, we need to get an idea of how many molecules are present. So, we have a couple of things. First off, standard temperature and pressure. Okay, well, how do we abbreviate that? STP. Okay, what is standard temperature? Two something, is that what I heard? 273 at 0 degrees Celsius, which is equal to 273 K. That's standard temperature. What's standard pressure? I heard somebody say it. 1 atmosphere. And how many millimeters of mercury is that?
760.
Which is the same as 760 torr. All right. So these are things you just have to know that standard temperature and pressure. And that just because gases can expand and contract based upon, the pressure and temperature, the volumes, it doesn't have a constant volume. We have to specify a set pressure and temperature in order to be able to compare, one gas to another, how much is there. So, we have this thing called the molar volume. Now, just based upon the title or the name, what do you think the molar volume is? Volume of 1 mole of a gas. One mole of any gas at STP. And what does that equal?
20 something.
22.4 liters per mole. Not quite sure how it made it back here. But this box is actually, the volume of this box is 22.4 liters. It's hard to believe that you could put over 11 2-liter bottles of soda into here, but you can. Okay, I measured it on many different occasions, and just because it just seems too small to be 22.4 liters. But that's how much. So in other words, if we have this filled with gas, and we get the temperature down to 0 degrees Celsius, and we have normal 1 atmosphere of pressure, I would know that there would be 1 mole of the gas inside of here. Now, does it matter what the gas is? Okay? No. Because of Avogadro's principle. Avogadro's principle. Equal volumes of gases under the same conditions of temperature and pressure contain the same number of molecules. let's just assume these are two different gases. Hydrogen, helium, carbon dioxide, oxygen. Equal volumes, pretty close. That means there's the same number of molecules in each balloon. Now, why doesn't the size, why doesn't the type of molecule matter in a gas?
Because it's not about the size of the molecule, it's about how they hit the walls of the container.
You're 50% right. It's not about the size of the molecule, but
They're so spread apart.
they're so spread apart, the size of the molecule is insignificant. Okay? They actually consider the molecules of a gas to be point masses, have zero volume. The total volume of the gas is the space between the molecules. So it's kind of like, nowadays you go to the stadiums and they're only 20% occupied. So it doesn't matter if it's, a big, heavy 500-pound person in there versus a, 100-pound person, because there's plenty of room to spread out. Okay? But if you're on Southwest Airlines and, you have that one middle seat between you and you see this big person coming down the aisle, you say, oh God, please, not in my row, because you don't want to sit, just all kind of crammed together. Now, I don't like somebody in the middle row, period. But, it's just, there's plenty of space. So the size of the molecule. So Avogadro's principle says equal volumes of gases under the same conditions of temperature and pressure have the same number of molecules. Therefore, the volume and moles are going to be in the same ratio. So when you're doing a chemical reaction, it's going to take 2 liters of hydrogen to combine with 1 liter of oxygen to make 2 liters of water vapor. Because the volumes are going to have the same number of moles. So in gases, the volumes, we can treat them just like it's moles, because they're directly proportional to one another. And then if we make the conditions of temperature and pressure STP, we know that 1 mole of any gas then is going to occupy 22.4 liters. Now, if we change that away from STP, then it's not going to be this, but at the same conditions. So in other words, you're doing a reaction in a beaker or in a container, the pressure and the temperature are going to be the same, so therefore the volumes that are combined are going to be in the same ratio as the moles. So this is, for stoichiometry purposes, this is a very important equation. Okay? Very important equation. So, knowing all of that, where would I plug moles into this equation? How do moles and pressure relate? If I increase the number of moles, what happens to the pressure? It increases, right? So what type of proportion is that? Direct, which is going to be more along these lines, right? If I increase the number of moles, what's going to happen to the volume? It's going to increase as well, a direct proportion. So if I'm going to put moles into here, moles is going to go into the bottom because they're directly proportional with pressure and volume. So, turn it a little bit more out, please. If I say P1, V1, N over T1, now moles, this is a closed container, so moles isn't going to change at all. You can change the temperature and pressure and volume, but the number of molecules present isn't going to change. That just means that it's going to equal some constant K. Well, in the ideal gas law, what do we call that constant? R. So we can then say PV is equal to nRT at any conditions. This is known as the ideal gas law. So R is just the constant. It's the exact same thing as we've been doing here. We're just including moles. And, by the way, N equals moles, if you don't know that. Okay? I don't know. They've already used the M for meters and millimeters, and so M got overused, so they had to go to N. I don't know if there's any Latin word or anything for it, but N is always going to be mole. So, this is what we call the ideal gas law. R will always be given to you 0.0821 liter atmospheres Kelvin moles. Now, there is no constant on these. So pressure and volume can be in any units. Temperature always has to be Kelvin, but pressure and volume can be in any units here, because there's no constant. But because we're calculating a constant, the units here have to be, volume has to be in liters, pressure has to be in atmospheres, temperature in Kelvin, and N is always mole. Because we're using R. Now, there is also a different value, 62.3, 62.4, is there not a, how can I remember it, because I'm old. This is given to you on your equation sheet that you will have. And the value of R is given as 62.36. And that's going to be liters, millimeters of mercury, kelvins, mole. So in other words, if you don't want to change, if you're given the pressure millimeters of mercury, you don't want to do the conversion to atmospheres, you can use 62.36 as your value of R. Most people go ahead and just convert atmospheres, the millimeters of mercury to atmospheres, and then just use the 0.0821. But it really doesn't matter, okay? Both of these values are given to you on your equation sheet. You'll never have to memorize them. All right, so PV equals nRT. Pressure, volume equals moles. So let's just rearrange this a little bit to see what else we can find. How do I, if I'm giving grams, how do I find moles? Molar mass, right? So we could say that PV is equal to grams over molar mass RT. That's a more useful form because most of the time you'll have the grams of gas, not the moles of gas. But grams to moles we've done like a bazillion times already, so that should be a pretty straightforward. Okay? But now if I want to rearrange that, sometimes we want to find the molar mass. So we're going to have to multiply both sides by molar mass, right? You got to go back to algebra 1. Multiply both sides by molar mass. That's going to give you molar mass times pressure times volume is equal to GERT, GRT. But then to solve for molar mass, we're going to divide by PV. So you're going to end up getting GERT over PIV. Now, what does G stand for? Grams, which is a measure of mass. V, volume. What is mass divided by volume? Density. Okay? So we can say that the molar mass is equal to dirt over P. Because G over V is equal to D. These are not 4 different equations. This is just going to be one set of equations that's just manipulated and rearranged in a variety of different ways. But you can see how you can find out just about anything from this equation. Now, one more variation off of this, okay? If I want to do density, okay, what's density going to equal? If I want the density of the gas. Okay, so density is equal to pressure times molar mass divided by RT. Okay? Now, trying to figure out, there's the 22.4. I think the one I wanted was, molar mass is density, yeah. At STP, the molar mass is density times 22.4 liters per mole. This is at STP. This is the one I was going for. If we want to do this, R times T divided by P at STP, that's what equals 22.4. When you take the value of R times the temperature, 273K, divided by the pressure, 1 atmosphere, you're going to get 22.4. In other words, 0.0821 times 760 is equal, times 273 is equal to 22.4.
Can you move the 22.4 liter box?
Yep, just using the whole board. Okay, so that's all of our equations. Notice on these, how many sets of conditions do we have? Two, right? P1, P2, V1, V2. So you have an initial set, then you change to some new set of conditions. And you find out, how did the volume change when I changed the pressure? How did the pressure change when I changed the volume? On all of these, okay? So you have two sets of conditions. Given one set, what volume will it occupy at STP? Or if you add STP, what volume will it occupy at room temperature? How many sets of conditions do we have with the ideal gas law? Just one. And you know you're going to use the ideal gas law, number one, if you only have one set of conditions, and number two, if anything with grams or moles are mentioned. Because none of these involve grams or moles. You can solve just about any gas law problem with PV equals nRT. Thus, it's called the ideal gas law. All right? So we just need to practice some. Can you guys access your textbook through your Chromebook? Okay, once we do that, it's chapter 10.
Password time.
Just as I'm flipping through the book here, some of y'all may have been reading chapters 8 and 9 in order to kind of prepare for this test. I do want to say that the whole section at the very end about molecular orbitals with the pi and pi star, sigma star, we're not doing any of that. That's not on the AP test. We're skipping that whole section. So if you read that and were a little confused, that's totally fine. We skipped over that. Okay, but this is all chapter 10. Chapter 10 is a relatively short chapter. So this is the end of chapter 10 right here.
Yeah, the Wi-Fi's like, yeah, we're down again.
Really?
Well, it's like,
It says it's connected, but it's just not going anywhere when you
it's not loading anything.
We're getting DNF.
Alright, what does that mean?
Oh, because I can't read your
Oh,
No internet
We're
connection.
getting